then the diagonals of the parallelogram are congruent. So the converse is also true, meaning if you have a parallelogram with congruent diagonals, corner to corner are the same length, that means that parallelogram is a rectangle. So we're going to write this is called a flow proof here, or a paragraph. No, this is a paragraph proof. We're going to do a quick paragraph proof. We're going to fill in a couple things for it. Then we'll do a 2-column proof like we are more used to. And then we're going to do some coordinate geometry on the last page of the notes here. So here we go. It says that AB is equal to 50 feet. Let's go ahead and label this then. AB is 50 feet. BC is 20 feet. CD is 50 feet. AD is 20 feet. AC is 54 feet. And BD is also 54 feet. Prove that quadrilateral ABCD is a rectangle. So it does not tell us if the quadrilateral is a parallelogram, and it also does not tell us if it is a rectangle. We have to end up proving both. Because right above, it doesn't say that any quadrilateral with congruent diagonals is a rectangle. It says that a parallelogram with congruent diagonals is a rectangle. So in order for it to be a rectangle, we have to first prove that it's a parallelogram. Then, because the diagonals are congruent, which we can obviously see here, we can make the statement that it's a rectangle because of the fact that the diagonals are congruent. So let's take a look. By the way, the reason why a quadrilateral with congruent diagonals isn't necessarily a rectangle is because we have things called trapezoids. So just for quick reference here, off to the side here, if you want to draw this, you can, but you don't necessarily have to. But if I were to draw a trapezoid, and if I were to go ahead and get that diagonal there and that diagonal there, those two diagonals are the same length. The red lines are the same length. That's not a rectangle. So just because the diagonals are the same doesn't mean it's a rectangle in a quadrilateral. It must first be a parallelogram. So that's why we're being really specific about that. So is this a parallelogram? Why? Exactly. Opposite sides are congruent. We learned in our parallelogram section that, or actually it was lesson 7.3, tests for parallelograms. We learned in lesson 7.3 that if opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. That was theorem 7.9. So if both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram. With this example here, opposite sides A, B, and D, C are 50. That's congruent. Opposite sides A, D, and B, C are congruent. They're both 20. So that means we have both pairs of opposite sides congruent. And that's what this paragraph is saying. Because AB is equal to CD and BC equals to AD. And AD is, okay, all these are congruent. All right, that's because of definition of congruence. Because the opposite sides are congruent, AB is congruent to CD, BC is congruent to AD, that means that ABCD is what? It's a parallelogram. And you can just go ahead and draw the symbol for parallelogram. It's like a rectangle, but it's leaning. So it's a parallelogram because opposite sides are congruent. Then, because A, C, and B, D are congruent diagonals, that means it's what? So the parallelogram has congruent diagonals, which makes it a rectangle. There you go. All right. That's it for that one. Quick proof. So that's just kind of like making statements and talking through it, basically. We have a quadrilateral. And we have a quadrilateral. And the opposite sides of the quadrilateral are congruent, therefore it's a parallelogram. Because it's a parallelogram and the diagonals of the parallelogram are congruent, they're both 54, that makes it a rectangle. All right, let's go ahead and do a 2-column proof here. And again, with our notes, the statements over here, there are a list of statements, so we just have to choose the right statements from this list and put it in. So we're going to complete the proof with the correct statements. And we are told that PQRS is a rectangle. Okay, so that gives us lots of information. And that PT is congruent to TS. And we're supposed to prove that QT, this length here, is congruent to RT, this length here. So my guess is that we're going to end up using congruent triangles because, well, we know a lot of things about rectangles. So let's just kind of talk about what we can see here without necessarily referencing the 2 columns. So would you agree that in a rectangle, the opposite sides are the same length? They're congruent, they have to be, right? Okay. So that means that QP would be the same as RS. And would you agree that both angle P and S are 90 degrees? Yeah, because in a rectangle, that has to be true. So take a look at what we got here. I see 2 triangles, QTP and RTS. Are they congruent? Are those 2 triangles congruent? Yeah. Which of our triangle congruency statements? Side, angle, side, yeah. We got 2 pairs of sides congruent with the angle in between those 2 pairs of sides. So that would be side, angle, side. So we can prove that the 2 triangles are congruent by side, angle, side, which automatically means that those lengths are also congruent because of CP-CTC. Corresponding parts of congruent triangles are congruent. And that's essentially what this proof mentions. So we're told that it's a rectangle. We're told that PT is congruent to ST. That's given. PQRS is a parallelogram, definition of a rectangle. Why is that? Kind of weird, isn't it? It says PQRS is a parallelogram by the definition of a rectangle. Yeah, every single rectangle is a parallelogram. Therefore, by the definition of a rectangle, this has to be a parallelogram. It does not work the other way around. We can't say it's a rectangle because it's a parallelogram, but we can say it's a parallelogram because it's a rectangle. All right. Then this says opposite sides of a parallelogram are congruent. Hey, we already marked that on our diagram. So what sides would we say for that? What sides did we mark that weren't already marked as congruent? QP and RS. And if you look over here, RS is congruent to QP. That's one of the statements we're going to be using. So that's the one we want to use for statement number 3. RS is congruent to QP. Statement number 3. RS congruent to QP. All right, now we're going to use the definition of a rectangle to make a statement about look at the statements that we have over on the right. Which of those looks like it would be because of the definition of a rectangle? Yeah, because the definition of a rectangle from yesterday says, we've got it right here. It says a rectangle is a parallelogram with 4 right angles. So there are 2 things that we are told are part of a rectangle. First thing is it's a parallelogram. Second thing is all the angles are right angles. So that would be exactly what Zach just said. Angle S and angle P are right angles. So that's the statement there. Angle S and angle P are right angles. Cool. Because they're right angles, that means they're congruent. Because all right angles are congruent, because they're always 90. Bless you. All right. We mentioned side angle side earlier. So which of these last 2 would be for side angle side? Segments being congruent or triangles being congruent? Triangles being congruent. Yeah, side angle side is used to show that triangles are congruent. So 6, triangle RST is congruent to triangle QPT. All right. And then if you recall 2-column proofs, the last statement is always the thing you are told to prove, which is this: QT is congruent to RT. The segment QT congruent to segment RT, and that's because of CPCTC. If you forgot what that means, first of all, it stands for corresponding parts of congruent triangles are congruent. And what that means is, if you have proven that 2 triangles are congruent, whatever parts of those triangles that you haven't yet stated to be the same have to be the same because the triangles are the same. So that is our proof. And that's all for proofs for today. But if you needed to, you could probably work your way through most of these, I think. You know, the reasoning, it's all about reasoning. And the better you get about thinking about geometry, the better you'll get at reasoning through these things. So if you're looking through these right here and you're like, oh, this actually kind of makes decent sense, that probably just means you're thinking more about the logical step-by-step, like, oh, okay, I get that. As long as you can follow it and it makes sense, we're good. Because we're not going to do a lot more with proofs in this class. All right, turn the page. Let's keep going. So some coordinate geometry here. And we are going to be testing / proving things about the shapes on the grids that we're looking at. So you can also use the properties of rectangles to prove that a quadrilateral positioned on the coordinate plane is a rectangle given the coordinates of the vertices. By the way, it's not just rectangles. You can prove that it's a parallelogram. You can prove that something is a square or a rhombus or a kite or a trapezoid. Those are other shapes we're going to be talking about in this unit, by the way. Oh, hey, this is kind of what Alex was just saying a minute ago. Rectangles are parallelograms. All rectangles are parallelograms, but not all parallelograms are rectangles. Okay. So over here, you will be doing some of this on your assignment today. So follow along closely with this. Identifying rectangles on a coordinate plane. So GHJK has vertices, corners, at -3, 0. So there's G at -3, 0. H is at 3, 2, right up here. J is over here at 4, -1, and then K is down here at -2, -3. They put it on the graph for us. That's very good. Determine, here we go, you ready? Determine whether GHJK is a rectangle by using the distance formula. So here's what needs to be proved. And it's actually kind of works through everything, kind of tells us how to do this. We don't really have to do anything for this. So please follow along carefully since we're not really being asked to do much for this. So using GHJK, if we're trying to figure out if this is a rectangle, we need to prove first that it's a parallelogram. Now, this is one way to do it, using the distance formula. The way that I recommended a couple days ago, do you remember when we were dealing with this with just parallelograms? Remember a few days ago what my recommendation was? The slopes, yeah. Figuring out the slopes is probably the quickest way to do it. Because if you can prove that the slope of GK is the same as the slope of HJ and the slope of GH is the same as the slope of KJ, then that means the opposite slopes are parallel, which mean, or opposite slopes are the same, which means they're parallel for the opposite sides, which makes it a parallelogram. That would be my recommendation. So we'll go through this, and then I'll go back and kind of tell you how I would do this if I was given an option. So distance formula between G and H. We wrote down the distance formula a few days ago. That was the x2 minus x1 squared plus y2 minus y1 squared. And so between G and H, that's the top length here, we get all the math there, square root of 40. So if you do the math, you get square root of 40. And you don't need to simplify it to a decimal either. You can just leave it like the square root. HJ, the right side, ends up equaling the square root of 10. Now, it's not the same as the top, which doesn't matter because those aren't opposite sides. Those are adjacent sides. They're next to each other. KJ, though, is the one on the bottom. And the distance between K and J is the square root of 40, which is the same as the distance along the top between G and H, which is the square root of 40. And then GK on the left is also the square root of 10, which equals HJ on the right. So opposite sides are congruent, which means we have a parallelogram. So that's where we're at so far. Now, because it's a parallelogram, if we can prove that the diagonals are the same length, that means not only is it a parallelogram, it's also a rectangle. So it's a parallelogram. Now determine whether the diagonals are congruent. So that would be the distance from between G and J and the distance between H and K. If we can use the distance formula to prove that those are the same, then the parallelogram is in fact a rectangle. So here we go. GJ, plug it into the distance formula, you get the square root of 50. KH, same thing, you get the square root of 50. So yes, this is a rectangle because it's a parallelogram and the diagonals are congruent. However, the way that I would do this, because that's using the distance formula 6 times, there's no problem with that. It just takes up space and time. How I would deal with this is I would go with the slope method because we know that a parallelogram by definition has 2 pairs of opposite parallel sides. So if we can show that the slope between G and H is the same as between K and J, so let's do that. So if we figure out the slope here, we can go up 2 and over 1, 2, 3, 4, 5, 6. So 2/6 or 1/3. If we go K to J, 1, 2, 1, 2, 3, 4, 5, 6, 2/6 or 1/3. Top and bottom parallel. G to K, down 1, 2, 3 over 1, -3, or -3 over 1. H to J, 1, 2, 3 over 1, -3 over 1. So with that, we proved that it's a parallelogram, which is a lot quicker, I think, than using the distance formula. Unfortunately, if it tells you to use the distance formula, you need to do that, like on the assignment. I would go with slopes. Now, the other thing is, what is the definition of a rectangle? To the beginning of this lesson from yesterday. It's on the first page of this lesson. So go back and read the definition real quick. A rectangle. Yeah, it's at the very top where a parallelogram is in bold, or not, a rectangle's in bold. It's a parallelogram with 4 right angles, right? Now, right angle means what? 90 degrees, which means what? Perpendicular. Now, I don't know about you, but I feel like we have some information that we know things about slope that we can say is perpendicular or not, right? So if the slope between G and H is 1/3, and the slope between H and J is -3 over 1, are those slopes perpendicular? Zach is nodding. Why? They are opposite reciprocals, yes. Opposite reciprocal slopes mean perpendicular, which means that between G and H and J, that's a perpendicular angle, 90-degree angle, so there's a right angle. If we look at the slope between HJ, the right side, and KJ, the bottom, -3 over 1, +1 over 3, opposite reciprocal. So we got another right angle. Between the bottom, KJ and GK, 1/3, -3 over 1. Right angle, those are perpendicular. GK, the left side, GH, the top, -3 over 1, +1 over 3, those are perpendicular. So we have a parallelogram with 4 right angles, therefore it's a rectangle. That would be the way that I would prove it. If I was given the option of proving something to be a rectangle on a grid, I would probably do this every single time, because I find that to be quicker than using the distance formula 6 times. So that would be my recommendation if you are given an option. If you're not given an option, use the method it tells you to use. All right, last thing down here. A quadrilateral has vertices 2, 6, 3, 7, and 6, 4. Which of the following points would make that a rectangle? So let's just go back and use this grid here. It'll be kind of annoying because we're going to overlap some stuff, but I guess it's kind of the best we've got right now. So A is at 2, 6, which is right there, like above the grid a little bit. I wish they would have given us a graph to do this one. Oh, well. 3, 7 for B. Oh, that's even more annoying. That'll be like here. Okay. 6, 4 for C, which is like there-ish. All right. Where does point D need to go? What do you think? Would you agree that the distance between, here's point B, or I guess the way to get from B to A would be the same as to get from C to D? Does that make sense? So like if we go from B back to A, B is at 3, 7. A is at 2, 6. So if we go from here to here, how far down do we have to go from 7 to 6? Down 1. And from 3 to 2, we're going back how far? 1 again. So down 1, left 1. If we do down 1, left 1 here, from C to D, that puts point D right here, which is 5, 3. Is that one of our options? Yeah, it's option A. Now, we could have done a bunch of math to figure that out, but like, I don't know, take the path of least resistance most of the time, right? We don't need to intentionally make math more complicated than it needs to be. Sometimes we do just for the fun of it, but we don't necessarily have to. All right, 5, 3. All right. So that's it for the notes for 7, 4. Like I said,